Before I continue, I would like to make a very clear information is that although this is a closed loop function, it also has a multiple of b of s, okay, which is the one. So we already assume that bs is equal to 1, therefore we treat it invisible. But however, you should take note that you should, this is some feedback loop. If feedback loop has a certain value, you have to multiply it in. So you can just work it out why this view of s exists in the end. Okay, this is just if you were to do this thing and then you include b of s. Okay, if you do the same whatever that are derived you derive, but while you include b of s in this case. Okay, in this case, let's say you are talking about main input minus output. So output itself is ys multiplied by bs. So then you just do. Okay, this is not important. Okay, this is not that important. But the important thing is that let you know that the closure function. This is a closure function. Okay, so now you should know that this is a closure function now. And then open loop is just the numerator. Closure function multiplied by the feedback system, you will get some values of this is actually the transfer function. Okay, so transfer function consists of all these things. Just that because the feedback loop is equals to 1, therefore we ignore this and it's just like that. So this is a very important concept I would like to make known. So with this, let's start off with let's continue. Anyway, if you were to turn to this page, okay, this is the same descriptions as what we have derived earlier. Okay, so this thing derived comes from the very first video as we derive our relationship for within this system, the G of S, remember. So this thing is somewhat equivalent to this thing, okay? It's actually this. Well, however, you're talking about when you're dealing with ES, okay, we're dealing with this portion over here. So they actually the other approach is actually multiply K ES. It's the same thing like there's nothing much. There's nothing different from what we derive over here. This is a long derivation for this whole system, I would say. Okay. So if you were to say that this KES is equals to this, and then you sub it in, okay. So what does this mean? Okay. So this is simply K. Okay, hold on a while. Okay. So as I mentioned earlier, this part is the same as my equation 1. Okay, they are the same thing, they describe the same thing as you can see. Okay, it's just about the K. So if you were to use this equation, so this equation actually describes this is output is equals to K E S G S. So what is K E S G S? K E S G S. So they actually go in this manner. So how do I identify who is K, who is ES? So as you know, this thing is actually KES, right? This portion here is actually KES. The numerator is actually KES, while the 1 over S plus A is actually G of S. If you remember from the very early portion over here. Okay, so this all makes sense. So this part we also talk about it over here. So Y of S is equals to KES GS. It's the same thing. Okay, rather than cheat or failing, it's the same thing. So therefore, you can just rearrange. Okay, so eventually you'll get this one. So what is this one? Okay, this is actually KGS 1 plus kgs. So we have a step 10 now, okay? So we have a step 10 now. So this is actually step 11. So what is step 10? Okay? So step 10 is, hold on a while. So since we know that g of s equals to 1 over s plus a, so kgs 1 plus kgs is equals to k over s plus a divided by 1 plus k over s plus a. So now comes the tricky part. You multiply the whole equation by s plus a, so you'll cancel out this s plus a, and this one will become s plus a. So eventually you will have k. So you have, so this is s plus a plus k. So if you remember, you just multiply s plus a, you get this s plus a. You multiply the whole equation by s plus a, right? So this one multiply, this one will become s plus a, while this one multiply, there's nothing. So in fact this one is equals to this one. Okay, I mean this one is equals to this one, just that I rearrange only, okay? So they are the same values. So this is how I derive my 11. Okay, so is equals to y of s over d of s. So this is the input, the main input, if you remember, d of s, and the output is y of s. So therefore step 11 is this. Okay, and then now here, so as we say that y, okay, y is actually this thing. Okay, so the amount of energy, okay, is in terms of the amplitude y. Okay, so as I say earlier just now, the stored energy, the change in stored energy, the amount of water, if you were to have input power larger, okay, so you actually or maybe if the power loss is lesser, you will have a faster time to come spike up to whatever your desired value will be. So y is actually your desired value. Okay, so therefore your output itself can be said as y. So Laplace transform of any constant is y over s. Okay, 1 is equals to 1 over s, 2 is equals to 2 over s, a is equals to a over s, nonetheless, so y is equals to y over s. So this is just a Laplace transformation. So as we can see, after our step 11, okay, we bring our input, okay, up here. So our input is actually y over s in this case, because we want our input to be eventually our same as our output. So this input is actually a step input. 1 over s is step input. So y is the magnitude of our input power, how large the y is. So just to make clear, just now I say this y is the output. So yeah, I am wrong. So the y is actually the input. Okay, so this y is actually the input. The input. Okay, so y over s. So this, in other words, this is y over s. So if you multiply in, you have this one. This is where it is. And then you do a partial fraction. So this is a partial, I mean, it should be partial fraction. Oh, sorry, this is, yeah, it should be partial fraction. And if you do partial fraction, and then you, now you have a partial fraction already, you can change it to time domain. So you just simply divide, so this portion simply divided by k. So if the whole equation divided by k, you have 1 plus a over k, and this is the relationship for closed loop. And then so the power consumption ut of this portion over here for a controller can be modeled as this equation or this thing. Okay, where a is the amount of power losses. If you remember, this is a, right? This is a. So everything is amount of power losses. So the larger amount of power losses will have will reduce the amount of power consumption. So we try to minimize the A. As we say, we minimize the power loss, we will have something. So this is okay. So actually, this is not this. They are different. So let me see. Hold on. So this thing, okay, as I just now read my notes, this thing is actually the closed loop response. Okay, we also saw call it the step response because you're multiplying 1 over s with magnitude y, so it's y over s. And then the power consumption is just it's ut itself. So it's over this portion over here. So it takes on es and k, and then so es is in terms of the relationship between ys and ds, the input and output, and then with k. So this is just I don't know how to say this, but I also don't know whether it is important. So it will be for you to find out. And nonetheless, I will just touch up the last one, which is this. So if you take a quick look with the open loop and closed loop comparison, closed loop you're having this the response. Okay, this is the this thing is the response. Okay, so step response, you have a much fast you take a much faster time to actually reach our output, our desired output. While the open loop, having the equation, this takes a slightly exponential time. So it's slightly so this portion over here, this difference, okay, I think you will understand what I mean. This differences is actually the power losses. So apparently open loop has a lot of losses. So this y closed loop is much good because we have a feedback system to control the amount of losses. As we have discussed earlier for this thing, where when it starts to fill up, flow up, you have a lot of losses, which is not cool. So this is comparing input, okay. So the input itself, it's when you're talking about this portion over here, okay, a multiplied by y and 1 plus a over k. So your input itself, it's okay. So ay, so what is ay? Ay is actually the power losses. So from this equation, I don't know how it works, but apparently it's just showing that the amount of input, okay, the amount of input, it's significantly reduced. I mean the amount of power loss is significantly reduced, much significantly reduced. Okay, compared to, there's no comparison, but this is just saying that the closed loop itself. So the closed loop itself can actually reduce the amount of power losses. So so the power losses for, I think this one is this dotted line, it's actually the, yeah, whatever. So eventually our power losses is actually much lower from this case, I say. So yeah, go on. So the speed, okay, the speed increases with k, okay. So when because 1 plus a over k, so k itself, if you were to multiply by whole equation by k, so it will be ky. Hold on. So if you were to rewrite this thing, okay, this thing into this, k, when k is gonna be higher because you're multiplying with the amount of output, you're actually multiplying is grows faster than adding. So therefore the k itself, when it's higher, okay, the speed is actually increased. So the time taken is actually increased. So the offset also reduces with k. So yeah, I don't know what we did. And then hold on. So in the future, okay, well, I'm not gonna talk about it. So maybe in the future you may need to come back here and then go and check it out. Okay, I will suggest you come back here and read this out when you finally understand the full meaning of how K will influence the closed loop and open loop thing. So if you were to still return back, okay, if you remember, as I said earlier, this one is the open loop and this is the closed loop. And as I say, denominator wise, this is the poles, this is the zeros, okay. So the poles and the zeros, the is all influenced by k. So the control itself is very important, and nonetheless a transfer function. So in the future we'll talk about that. And I think I'll just clear all this. So you can actually go and read out for this one. Okay, this equation is the same as my analogy for here. So it's just the amount of heat within the material plus the amount of heat lost to the environment is equals to the amount of heat input. And then the rest of the situation, you just switch it to Laplace. Okay, so this thing you just change to Laplace, and then you do some shit, and then you get something. That nonetheless there is also water. So my case is different from this case, so I believe this one is much better than my example. So you should go and take a look. Okay, so I'll just do a quick summary for lesson 1. I've took a very long time, so hopefully I can clear all these things. So I shall see you there.